rate laws tell me the speed at which a reaction takes place. The rate is equal to K times the concentration of my reactant raised to the power n. K is the constant, or it's called the rate constant, and that essentially tells me the probability at which a reaction will take place. K is unique for every reaction, and also it changes depending on temperature and the set of environmental conditions. And later on we will learn how K is affected by the different environmental conditions. But K is also affected by what the molecules are. And I said the best way to think of it is the probability in which a reaction takes place. And some things that might affect that probability are the energy needed to overcome between the molecules in order for a bond to form. Also the orientation of the molecules in order for the reaction to take place. Here's an example on the right. If these collide this way, the reaction will take place. If they collide this way, the reaction will take place. But if they hit each other this way, then there's no reaction. So depending on the shape of the molecule, it can have a big effect on the rate of a reaction. That is why in biology so many catalysts are needed, because we'll have very large, bulky organic molecules, and the reaction site will be a very, very small and specific area. So in order for it not to take 1,000,000 years for it to take place, or need an absurd amount of other reactant, then what the body does is use a catalyst and targets them specifically. And the N, this is the order of the reaction, and it has to do with the reaction mechanism. And I wasn't going to go over it that much, but I may as well. In this section in general chemistry, we're mainly going to learn about first order, second order, and zero order reactions. And, yeah, I guess I'll just do some examples, why not? So why this would affect rate? Well, let's have a look at what would happen first if I put in a 1, 2, or 0 for rate. If I put in a 0, then the rate is equal to just K. The 0 raised to the 0 power is 1. If I put in a 1 in here, then the rate is going to be directly related to the concentration of A. If it's to the second power, then it's the square of it. So why does this happen? Well, let's look at some example reactions. I guess I'll do a zero order first. So zero order, essentially what a zero order is telling me is that rate is equal to K A to the 0, which is equal to just K. So it is equal just to whatever the rate constant is. It is not dependent on the concentration of the reaction, or the reactant. The reaction is not dependent on the concentration of the reactant. So an example of this might be something where there's a catalyst. Say this is a platinum catalyst. It has a specific surface area, so only a certain number of molecules can be on the surface and react with this. Think of it as like if I'm baking cupcakes and I have a tray of 6. It doesn't matter how much cake batter I have, it doesn't matter how much reactant I have, I can only make 6 at a time. That's basically what a zero order reaction is. Now for a first order, basically equal just to K concentration of A. So the rate is dependent on what the concentration of A is. An example might be an SN1 reaction for organic chemistry. I guess it seems a bit ridiculous to go into this since this is organic chemistry and not at all related, but an SN1 reaction is something like where I've got actually, we'll just make it really simple. Why am I even going to do that? It's something like an SN1 reaction where a halide will leave and then a nucleophile will come and replace it. And I guess that doesn't really mean anything to anyone at this point, but what the idea is that this leaves on its own. This would be something, you know what, I can just do an example. We'll do something like this. So say I've got a chlorine here. Everyone knows that chlorine is extremely electronegative, or whatever it's called. It's got a propensity to draw electrons. So what can happen is that this chlorine can overpower. And it wouldn't happen like this. I'd need more. These would all have to be carbons as well, but just forget about that for now. Just pretend that this chlorine is strong enough and it gets to withdraw these electrons and it goes away like this. Now this is unlikely to happen because these are hydrogens, but don't worry about that. Normally it would need to be surrounded by other carbons, but who cares for now? I don't feel like drawing a whole bunch of stuff. It'll take too long. So the chlorine leaves this carbocation. So this is it's a strong electrophile is what they call it, and that means it has a strong tendency to draw electrons to it. So what happens is that a nucleophile will come along. A nucleophile is something that has a strong negative charge. Could be, I don't know, it could even be like a water or something like this. So this area is very negative. So what will happen is the chlorine might draw, this carbocation might draw this in here. And eventually leave me with an alcohol or something. Probably should have prepared. Actually, I wasn't even planning on doing something like this example, but. And then this extra hydrogen will be on here, then another water will come over and take away this hydrogen, and then I'll be left with this. And then an acid, basically. But the point of this whole thing is that the rate is dependent on this chlorine leaving. So this is an example of something where the rate is entirely dependent on this reactant right here, because the rest of this reaction cannot take place until this chlorine leaves. This is the rate limiting step. So in a situation like this, since the reaction is dependent on one molecule or one of the reactants, it would be a order 1. And then finally in order 2, I mean, I hope this isn't a complete waste of time, but it probably is for people who don't know what that is. But so something like this, and this would be similar to an SN, is it SN2? This is an SN1. And an SN2, this one's much easier to explain. This is, let's say, now this X means a halide, so it would be like chlorine, iodine, bromine, one of those kind of things. And then don't worry about what this other stuff is attached to, just pretend it's whatever you want. In an SN2 reaction, the nucleophile, which is something that is negative, something that has a lot of electron density, let's say, it's going to attack this end back here, because this halide, well, it doesn't have to be negative at this point, but it's drawing a lot of the electrons to it. So this end has a partial positive over here. So as a result, this negative is going to be attracted to the positive end, and what's going to happen is it's going to attack this carbon from the back. And then as this negative starts going towards this positive, this carbon is going to start relinquishing control of these electrons over here that are attached to this halide. So what will happen is something like this. And the point of this is, in order for this reaction to occur, it's going to be dependent on the concentration of the nucleophile and the concentration of this right here. So it will be a second order rate reaction. And it would look like this. So the overall rate would be 2, because this would be a rate order 1, and this would be a rate order 1 as well. And then when I add them together, it's 2. If something was reacting with itself, then I don't know, let's just say I had just X plus X gives, I don't know, something like this. Then this would be a second rate order as well, something like this, because it's dependent on the concentration of, or I can think of it like this. And the overall rate is 2. But that's just a basic idea of what's going on with the rates. K is, think of it as the statistical likelihood that a reaction will take place for a given set of environmental conditions. And then the N is just the reaction mechanism. What does the concentration of the reactant have to do with the rate of the reaction? So K is the probability that it will happen. Think of like burning of paper. Burning of paper, it's energetically favorable, happens very slowly. When I increase the temperature, that affects K, and K will go up. The statistical probability increases. So at higher temperatures, the paper burns faster. It bursts into flame immediately. At room temperature, it happens very slowly. It's impossible really to see the effects of burning paper unless I go to a museum and I see a book that's been on a shelf for like 300 years. Then I can see the pages are yellow and they're slightly burned.